Hey, welcome back to Graph Theory. In this lecture, we're going to continue looking at some ideas that are in section 6.1 on vertex colorings. And in particular, I want to tell you about something called independent vertex sets and the independence number. So you're looking at the goals of the lecture there. I want to define this independence number. It's denoted by beta of G. And then I want to use it to get a couple of bounds on the chromatic number, the minimal number of colors necessary to properly vertex color our graph. And then we'll end with a quick discussion of something called the greedy algorithm for vertex coloring. So it's kind of a systematic way to vertex color any graph, although as we'll see in our example, it might not necessarily turn out minimal vertex coloring. Okay, so let's get started here. Here's the kind of main definition of an independent set. So I've got an example there below, but so given a graph, you take some subset of its vertex set, just call it S. So I'm going to call that subset independent if whenever you take two elements of it, they're not adjacent. Okay, so an independent subset of vertices is just a subset of the vertices, no two of which have an edge between them. So I've got a graph G here drawn. I've just labeled a couple of independent sets. So first of all, in red, those 5 cut vertices, you can stop the video and verify that each vertex that I labeled red is a cut vertex. If you removed it and the edge is adjacent with it, it would disconnect the graph. And they form an independent set. It has 5 elements in it because, well, no two of those red vertices have an edge between them. I also colored, there are 8 vertices of degree 2 in that graph. I colored them all blue. They're also an independent set. Yeah, they're an independent set because no 2 blue vertices have an edge between them. The union of the red and blue vertices aren't an independent set. Yeah, you can see that like some of these blue and red vertices have edges between them. So together they're not independent. So independent sets, there's lots of them in general in a graph, right? And they can have different sizes. So it's a very natural question, given that the graph has just n vertices, how big can an independent set be? How many vertices in a graph can you choose so that no two of them are adjacent? Well, certainly it depends on the graph. It depends on the graph. So that's our kind of definition. The independence number, this beta of G, it by definition is just the size of the largest independent set. And there could be in general more than one independent set with size beta of G. That's a different question. But of all the independent sets, they're certainly no bigger than the order of the graph itself. And so there's got to be a biggest one. And that biggest one is the number is denoted beta of G. It's called the independence number of the graph. So what can we say about our graph up here? Well, from our work so far, I could tell you that its independence number is at least 8. Because I found the blue vertices, the degree 2 vertices, there's 8 of them and they're an independent set. Maybe its independence number is bigger. Let's make some just kind of quick observations here about this stuff. If G is non-trivial, that means it has at least one edge, yeah, and it has n vertices, well then its independence number is bounded above by n minus 1. Yeah, because if you have at least one edge, then there's at least a pair of vertices that are connected, and so the best you could do is that that there are at most n minus 1 vertices that aren't connected. So the biggest that you could have the independence number is n minus 1 for a graph of order n. You can actually achieve that if you take a look at the complete bipartite graph K1 n minus 1. It's usually called a star graph. I've drawn K1 4 over here. The complete bipartite graph K1 n minus 1 has order n. There's n vertices, one in the one of the partite sets, and then the n minus 1 vertices in the other partite sets. So together there's n of them. So the complete K14 is an order 5 graph. And you can see that the vertices that comprise sort of, I don't know, leaves, if you like, in this tree, they form an independent set, right? No two of those things are adjacent. And that's basically as big as the independence number can get. The smallest the independence number can be is 1, and that's achievable. The complete graph Kn has independence number 1. Any two vertices are adjacent. So the largest subset of vertices that you could find with no adjacencies is just take a vertex. Take a vertex. So adjacency doesn't even make sense. I'm going to leave this to you, but I think they're kind of fun exercises. See if you can come up with formulas in terms of n for the independence numbers of the cycle, Cn, paths, Pn. Fun exercises. All right, another good exercise that I'm going to leave to you, stated in your book, this graph G that I used above, the author claims its independence number is 11. So supposedly it's possible to find a subset of that graph. That graph has order 18. If you want to stop the video and count, the order of this graph is 18, and the author claims that you can find a subset of vertices that has as many as 11 vertices in it, no two of which are adjacent. So I'm going to leave that as a challenge to you to find that independent set of size 11. All right, let's take a look at a proposition here. It's kind of an interesting result, but if you take a graph G and you take any independent set, maybe we can try to leave this graph up there while we're looking at it. Take a graph G, take any independent set, so maybe it's my blue one that you're looking at. And then you let X be the complement of S in the vertex set. So our X in that graph is just the vertices that aren't colored blue. Okay, so that's what this thing is. And then the proposition says that if you take any edge in the graph, then it's incident with some vertex in X. It's kind of a neat thing. So stop the video for a second and look at this graph. But if you look up there, pick any edge in that graph, and it is incident with a vertex that's not colored blue. Any edge. Some edges are incident with two vertices that aren't colored blue, but every edge has at least one white vertex on it. Yeah, that's what this theorem is saying. It's because S was an independent set. If you want to stop the video and go back and look at the cut vertices, or if you've already found the independent set of size 11, you can check this out too. It works for any independent set of vertices. So why is it true? Well, let's take a look at the proof. It's actually a pretty short proof. Suppose that you took some edge in this graph, call its vertices U and V, and suppose that neither one of them were an X. Kind of looking for a contradiction. Okay, well, X is just the complement of S. So if U isn't in X, then it must be in S, and the same for V. So if they're both not in X, then they're in V, but they're adjacent. There's an edge between them, and S is supposed to be an independent set. So that's a contradiction. Okay, so that's why. It's a short proof. It's an interesting fact. The complement of an independent set is incident with everything in some sense, edgewise. Cool. Okay, so sorry for scrolling, but I'm going back up to see my checklist. We've defined the independence number. We've looked at a couple of examples, and now I want to derive a couple of inequalities, lower and upper bounds for the chromatic number that involve this independence number. Okay, so I've got two lemmas down here, and let's scroll to where we can see the first one. Good. Okay, so what does the lemma say? You take a graph of order n, then the chromatic number of that graph is always at least n over the independence number. This I'm not claiming is an integer. Most of the time, n over the independence number is not an integer. So if you want an integer right there, then you would put the the ceiling, I guess, because you'd have to round up. The chromatic number is an integer. Cool. All right, well, let's see if we can't understand why this is true. So just for shorthand, let's call the chromatic number of this graph K. So it's the minimal number of colors necessary to properly vertex color the graph. And then for every I between 1 and K, I'm thinking of the numbers 1 to K as the colors, if you like. So for every color, I let V sub I be the set of vertices that have that color. All right, so if you're literally using colors and say red was the first one, then V sub 1 is just all the red vertices. If blue is the second one, V sub 2 is all the blue vertices, and so on. Okay, those are independent sets for every color by definition, right? Because if you've properly vertex colored a graph, no vertices of the same color have an edge between them. So those VIs are always independent sets, yeah? And because of that, each one of them couldn't be any more than the independence number in size. The independence number is the maximum size of an independent set. And they also partition the vertex set of the graph, right? Because no vertex gets more than one color, but every vertex gets a color. So together the VIs union up to give the vertex set, and they're disjoint. So if you sum their sizes, you have to get n. You wouldn't do any double counting. You have to get the order. But every one of those numbers is less than or equal to beta of g, so that you end up getting n is less than or equal to k, the chromatic number. That's how many summons we would have times beta of g. So then just divide both sides by beta of g. Remember that k is the chromatic number, and there's our inequality. Cool. All right. Second lemma is another inequality. It's going to help us get an upper bound on the chromatic number. The second lemma is that if you take a graph of order n, then an upper bound on the chromatic number is the order minus this independence number, well, plus 1. Okay, so let's see why that's true. So take an independent set of maximum size. So take an independent set with a beta of g elements in it. And then let h be the graph that results from g by deleting those vertices. And of course, the edge is incident with them, right? So I claim that the chromatic number of h is at least the chromatic number of g minus 1 because of s's independence. So how to convince you of that? Well, I'm trying to convince you of this. Imagine that we have properly colored the graph h with chi of h colors, all right? And then we're going to stick the vertices in S back in. Well, since no two elements of S are adjacent, every vertex in S can get the same color. And if necessary, we could even use a color that we didn't use when we colored H. We might not have to, but worst case scenario, we could just pick a new color. So the chromatic number of H plus 1, the new color for the vertices of S, would certainly be good enough to color the graph G. We might be able to do it with fewer. So if you like, you could kind of think what I just argued is that chi of H plus 1 is greater than or equal to chi of G. And so just subtract 1. All right. Also, the size, the order of the graph H, well, it's n minus beta of g, because that's how many vertices we took out. And the order of a graph is always greater than or equal to its chromatic number, right? You never need more colors than you have vertices to properly vertex color a graph. So if we stick those together, if we take our sort of smallest number here, chi of g minus 1, we said it's less than or equal to chi of h, but that's less than or equal to n minus beta. Well, just ignore this middle part, and we get the desired inequality. Adding 1 to both sides, I guess. So chi of g is less than or equal to n times beta of g plus 1. Okay, so those two lemmas together prove this theorem. It's an interval that's guaranteed to contain the chromatic number. The chromatic number of a graph is always at least n over its independence number, but it's never more than n minus the independence number plus 1. Cool. Let's look at our example. Oh, where'd it go? I've got a graph gone missing. It's okay. I'll just bring this down there. I thought I had it down there already. Come on. Lemma theorem example. Here we go. There it is. This graph has order 18. It's written twice now. The author claimed, I'm hoping that somebody is going to verify it, that its independence number is 11. So if we use our theorem, we get a bound on the chromatic number. 18 over 11 is a number between 1 and 2, so the chromatic number would have to be at least 2. 18 minus 11 plus 1 is 8. All right, well, that's not the greatest bound. It's a pretty wide interval to say the chromatic number is between 2 and 8, but it's better, you know, I mean, the graph of order 11, worst case scenario, its chromatic number could have been 11, so this is not super sharp on the upper bound, but cool. All right, so that illustrates the independence number. And that was the main purpose of this. We're going to spend one more day talking about uniquely colorable graphs, and the independence number will be related there. But for now, I'm going to end this with just kind of a quick discussion about a systematic way to color graphs that's called the greedy algorithm. So let me put it up here. So, and I borrowed this instead of writing it out from Professor Isabella Khanna down at Sonoma State and her wonderful graph theory workbook. So this is Isabella Khanna's statement of the greedy algorithm. So let's take a look at what it says. So you have a graph of order n, and when you begin by listing the vertices in some order, all right? So you list the vertices x1 to xn. You can see in our graph G, I've done that. So here's your x1, x2, and so on. I just kind of went left to right and then row by row. So there's the 18 vertices randomly, in some sense, ordered. Okay, and then you also sort your colors into an order. So I've got pessimistically over here 18 colors, and then because I don't want to use numbers, I like the actual using of colors. So I went with 1 is red, 2 is blue, 3 is green, and so on. But you sort the colors in an order too. And then the algorithm says, okay, you give vertex 1 color 1. So there it goes. And now how does this algorithm go? You look at each vertex one at a time, and you basically look at the vertices that have already been colored that are adjacent to it, to xi, and you give xi the smallest color that you can that's not already present in the ones that are adjacent to it. So in other words, you choose the smallest color for xi that doesn't break the coloring rule. All right, so let's start trying to use this here. So we've colored x1 red, and now we move on to x2. x2 is not adjacent to x1, so it can also be red, smallest color possible. Now we move on to x3. x3, I have to look at x1 and x2, they're already colored. x2 is adjacent to x3, so the smallest color I can use is color 2. Now I move on to x4. Okay, x4 is, I've got to consider 1, 2, and 3. It's only adjacent to 3. The smallest color I can give x4 and follow the coloring rules is color 1. Okay, now we move on to x5. Let's keep doing this for a little bit here. Move on to x5. The smallest color that I can assign x5 is blue. Can give it color 2, right? Okay, how about x6? The smallest color that x6 could get is color 2. Finally, here's a little bit of action. x7 is adjacent to 2 previously colored vertices, yeah? So the smallest color that x7 can get is green. So I think I'm going to stop. I would encourage you to stop this video and continue. Use the numbers if you don't have a box of crayons. I hope you have a box of crayons, but if you don't, use the numbers and continue to color this graph, okay? I've got it kind of loaded down below. Well, I think I do. I don't know. This video is kind of taking on a mind of its own, but I worked this out beforehand. I just continued along. Should we do one more? What color can we give x8? x8 is adjacent to just x3 in the previously colored vertices, and so x8 can get minimal color red. Yeah. What about x9? x9 can't get red or blue, it has to get green, so on. So continue this. Continue coloring this graph. Just march through x10 all the way up through x18, always choosing the smallest color that you can that is not present in the neighborhood of the vertex that you're trying to color. All right, and it will be guaranteed to color the graph. Let me show you what I think it looks like. So I just continued on coloring that thing. X10, the very next vertex, had to get a new color because it was adjacent to the 3 previously used colors, so it got yellow. And then I just continued. So you can check my work here on this thing. And what can I conclude? Careful, I cannot conclude that the chromatic number equals 4. I 4-colored this graph. This graph has 3 cycles in it. It's got lots of them. So if you want, we could sharpen the estimate above, right? Our theorem was telling us that this chromatic number was between 2 and 8. It's not the greatest theorem in the world. This greedy algorithm tells us that it's no more than 4, and because it's got a 3 cycle in it, it has to be at least 3. Yeah. But the greedy algorithm that I just showed you is not guaranteed to produce a minimal coloring. So the chromatic number of this graph is still up in the air. The greedy algorithm, unfortunately, the coloring that it produces, well, it depends on the way you ordered the vertices. This particular graph would have 18 factorial different vertex orderings. And so even in terms of computational complexity, there's n factorial ways to order the vertex of a graph. So an algorithm that's going to kind of check all of those and then compute the coloring and to get the chromatic number, I think there's probably better things out there than that. But this is at least one way to systematically color a graph if you're not interested in the chromatic number, and it would always give you an upper bound on the chromatic number. Okay, so I want to kind of keep this a little bit short. I'm going to end it here, but I just kind of want to ask you, maybe you'd stop the video. Do you think we could three color this graph? So in looking at it, like that yellow vertex, is there any way that we could have avoided having to use that fourth color? I think so. This is the coloring that was dictated by the greedy algorithm. I don't think we violated the algorithm. But if we had sort of made a different choice, the reason we had to use that yellow is, well, kind of a virtue of the fact that we got to X10 after X9, X4, and X5 had already been colored, and they had those three distinct colors. But I don't think that that would have been necessary. I don't think it would have been necessary. I think you could probably have made a different choice right here, not by the greedy algorithm, but just by the human mind that would have allowed you to avoid that fourth color. So stop the video, think about it for a second, but I'm going to warp ahead in time and just show you there. There is a three coloring of this graph. I didn't need that yellow. If I would have labeled X5 with the color green, I would be violating no rules. I wouldn't have, marching along greedily. Green is too big. The greedy algorithm made this blue because its only neighbor was red. But if I had made it green, then I would have been able to make this one blue, and it's still a colored graph. So the chromatic number of this graph is actually 3. Okay, thanks for listening.